Welcome to the coronavirus lecture number 1, gravitation. So what you can see here, guys, is that this is actually Newton's universal law of gravity, where we've got this big G right here, which is a universal constant, and we have the one mass and we have the second mass. And then the r that you see in this equation is the distance between the center of those two masses. And so this is the brilliance of Isaac Newton, is that he saw this relationship happening in the heavens, right, with our solar system and whatnot. And he said, okay, well, maybe that's the same as what's happening on our Earth. You know, the proverbial apple falling on Newton's head. And it just so happens that this universal law of gravity applies both to our solar system and to the surface of our Earth, because what you will see is these three variables: big G, which is, again, the universal gravity constant, the mass of the Earth, and the radius of the Earth, all wrap up into one. And because each of them doesn't change effectively, even though the radius does move a little bit up and down depending on where you are, like if you're on a mountain or not, but it's pretty trivial relative to the actual measurement of the radius. If you combine all these three, right, all these are constants. And so if you wrap them up into one, you get an expression for the acceleration due to gravity. And what you will find is that if you plug in all the numbers for Earth, so you've got your universal gravity constant, the mass of the Earth, and the radius of the Earth, guess what you get? You get equals 9.81-ish. Right, depending on where you are on the planet. So there you go. That was the brilliance of Sir Isaac Newton. Okay, now to go over 3 realities of gravity on Earth. So AG, or the acceleration due to gravity, doesn't perfectly equate to G. And you might ask why. Well, 3 main reasons. Reason number 1, the Earth is actually not uniform density. So depending on where you are, the material underneath you can have more or less mass relatively. For example, in Canada has a huge deposit of iron underneath it, and so you actually weigh a little bit more in Canada than if you were somewhere else. Okay, so that's reason number 1. Reason number 2 why gravity doesn't work perfectly is that the Earth is actually not a perfect sphere. It actually bulges at the equator, thus more mass is closer to you at the poles, which is kind of interesting, or you're at least closer to the center of the Earth. You can imagine what happens here, right? If you ever have spun something really fast, you notice that it bulges at the equator of the rotation. And so the same thing happens with the Earth, although it's really not that significant of a bulge. Okay? And then number 3, the Earth itself is rotating. Okay? And it's rotating at a constant angular velocity. And so if you're at the equator, and we've talked about this when we went over like angular motion and circular motion, okay? When you're at the equator, you're actually moving faster, and therefore your centripetal acceleration required to keep you on the surface of the Earth has to be higher. Versus the poles, right? The poles, you're barely moving with any velocity at all, and therefore the centripetal acceleration required to keep you on Earth, right, is actually less. All right, now let's answer a question that I'm pretty sure you were dying to ask, right? What happens if a person, let's say, travels to the interior of a planet? what happens to gravity? Well, I'm not going to explain the math behind it, but I will explain actually what happens. Okay, and so what happens is that if you travel towards the interior of a planet, all of the material that's above you, so let's say you made it to right here. Woo! Okay, let's say you made it to like right here. All of the mass in this shell, right, this spherical shell, does nothing to the force of gravity. Okay, and so this would be an example of, it obviously doesn't exist, but let's say it's just a spherical shell and you're inside of it. Think about if you ever played Super Mario World, right? Or was it Mario Galaxy? I think it was, right? Once you're inside, you would have no forces acting on you because all this material right here, okay, all the forces of gravity would cancel each other out. And so if you were inside, right, this sphere, the forces created by the mass that's closer to you would be perfectly canceled out by all the forces that are further away, even though there's more of it kind of on this side. And so the net of those forces would actually add up to zero. It's kind of a weird little special case, but it works. Okay, so let's ask ourselves the question then, what actually happens to our FG, okay, as you quote unquote travel towards the center of a planet? It's not as obvious as you think it is, because as you travel towards the center, there's less mass that's acting on you. Think about it, right? All the mass above you basically nets out to zero, and so it's as if you're sitting on a planet that is slightly smaller. You see that? Okay, so all of this would go away, and we would just have this smaller kind of quote unquote planet. All right, but we're also closer to that planet, and so this gets less, right? And this gets less. So which one wins? All right, well, let's find out. If you want to actually calculate the mass of that smaller planet, right? So here's our big planet right here. All right, if we want to calculate the mass of that, then we can do that, right? It's the density times the sphere, right? The volume of that sphere, boom, is going to give us the mass of this. Right, and where does this come from? This just comes from geometry right here, right? We got 4/3 pi r cubed, and so we're going to plug that into the equation for gravity. And what do we get? We get a nasty equation, but if you do a little bit of simple algebra, bada bing, we get this equation. We get 4/3 pi rho g r m. So then I ask you the question: what changes on any of these? 4/3 doesn't change, pi doesn't change, rho doesn't change. That's the density because we're assuming it's uniform density. Big G doesn't change. We're not switching universes. Okay, your mass doesn't change, and so the only thing that's changing is r. And so what does this tell us? As we get closer to the center of the Earth, right, that radius gets smaller. Therefore, my FG gets smaller as well, in a linear fashion, because we have FG versus R, not R squared or R cubed or R to the half power. All right, boys and girls, we're going to do a little bit of math here. If you recall, when I say work, you should be thinking immediately what? You should be thinking integral f dx. Okay? We also know, and I want you to kind of take this for granted, but if you go way back to when we talked about energy, I think it was last semester, you recall the work done by gravity on an object, okay? There was that weird little minus sign in there, okay? This is where this comes from, okay? All right, so what we're going to do now is we're going to combine these two, all right? And so I'm going to plug my expression for work into my delta U right here. Are you ready? Of course you are. Remember, you can always back up and listen to this video again. So that means that my delta U, and what I'm going to be doing is I'm going to be calculating the change in U from infinitely away to the surface of the Earth. All right, we ready? Where's that come from? That's simply what? FG. Okay? All right, let's take some variables out and let's do an integral. And so if we take some variables out, actually we didn't take any variables out, but we did do the integral, right? Because that's r to the -2, right? Because it's on the bottom there. And so if you take the integral of it from infinity to r, this is the expression. This is the interior expression. And of course, we know what this means, right? That means I'm going to plug in my r minus plugging in my infinity. You may be asking, really? We're going to plug in infinity? Well, yes, because if you divide by infinity, what do you get? You get big fat 0. All right? And so our U final minus our U initial is simply this expression right there. Negative GMM over R. Okay? Notice it's orange and it's boxed. That means it's important. All right? Now you may be asking, really, Mr. Horn? Why is that negative? All right, so you may be asking, why is U negative? Basically, what it comes down to is to make the math easier. All right, so we use as a reference point, and this is completely different than when we were dealing with U sub G on the surface of the Earth, right? We would choose a 0 to be a particular height, right? And then anything above that would be positive, so to speak. Well, when we're talking about orbital mechanics, right, and the way that satellites and planets work, there isn't really a down and up because it's all relative to each other, okay? And so what we do is we choose a different reference point. We're going to choose a reference point that is infinitely away. And at that point, my U sub G final is going to be 0. Okay, so it is 0 because it's divided by infinity because it's infinitely away. All right, so as an example, let's just do a sanity check. So my sanity check is I'm going to start right here, and I'm going to take my object and I'm going to go all the way out here. And so I'm moving, quote unquote, up and away from the Earth. And we know if that occurs from our previous experiences, that adds to your potential energy. So your delta U would be positive. So let's do it. And so if I have my delta U, I'm final minus initial. And so my final is what? 0. Minus my initial, which also has a minus sign in it. And so it comes out to be positive. And so my delta U in that case still makes sense because as I go from the surface of the Earth up, quote unquote up, my delta U will be positive, which is what we've been used to. All right, so it all comes out in the wash. It all works out, even though we chose this really weird infinitely away is equal to 0. All right, let's talk about orbital mechanics. Small change in discussion, but really the same thing. All right. Take a look at this phrase. Okay, get some weird artifacts going on there. So take a look at that phrase. Okay, what it says is if a satellite is under uniform circular motion with balanced force, like it's not changing uniform circular motion, so it's going at a constant speed around and around, such as a satellite, your FC is equal to the FG, period. Okay, so what does that mean? So there's my satellite, right? And by the way, we're always assuming that it's circular, except for when we get to Kepler's laws, but we don't do any orbital mechanics elliptically. Okay, we assume that everything's orbiting in a circle. And the AP exam will actually explicitly state that. All right, so we know that FC, sorry about that, FC is equal to FG. Well, what is FC equal to? If you recall, if you don't, you can look it up again or just trust me. Your FC, which is the sum of your forces, is equal to the centripetal acceleration, right, times the mass. And so there's your mass, and there's your centripetal acceleration, v squared over r. So F sub c equals mv squared over r. And we've learned in this particular lecture, right, that our universal law of gravitation is equal to g big M small m over r squared. These r's are the same. Now, if you do a little bit of math there, what do you get? You get this expression right here. Kind of hard to see. But basically, your orbital velocity is equal to radical gm over r, period. All right? As long as it's in equilibrium and it's under uniform circular motion. All right? Now you may be asking the case, well, what if the satellite has a velocity that's greater than the orbital velocity for its current altitude? Okay? So if that's the case, it will orbit further away from the planet. So U will decrease and K will increase until this occurs. All right? And so say I'm orbiting right here, right? Well, what happens if I'm out of whack? What will happen is that orbit will get further away. Okay? And so your U will increase and your K will decrease. And it kind of is weird because the further away you get, the less velocity you're going to have in your orbit. Okay? But that's basically the trade-off. Because as your U gets bigger, more positive as you get further away, your K in kind has to reduce. Why? Because delta equals 0. Okay? All right. Escape velocity. So escape velocity is basically defined as the initial velocity required, let's say, of a rocket, a rock, I don't know, a small penguin, I don't know, something like that, right? What is that initial velocity required so that it has enough kinetic energy that as it loses it as it goes up, it will eventually escape that particular planet's gravitation, or that star, or whatever it is, okay? So it is called the escape velocity. So it'll eventually get infinitely away. It'll just keep going, all right? And so as with most of these things, what are we going to start with? We're going to start with delta E equals 0. And as you see here, we've got all of our terms, right? We've got our, oh yeah, there's the mechanics for what's happening, right? So it has enough velocity that it just keeps going, all right? And so here's our delta E equals 0 equation. We got our final minus initial, so that's delta K, right? And then on this side, we have our delta U, our final minus initial, right? Well, we can plug some things in for that, right? So we're going to have our final velocity. We're going to have our initial velocity, which, by the way, this is going to be right here, what we're going to have to solve for, because that's going to be our escape velocity. All right. And then we're going to have our infinitely away U, and we're going to have our initial position away. All right. And so here's one of the key things to think about is that you want it to have just enough escape velocity that when it reaches infinitely away, it's basically not moving anymore. Well, not moving anymore would be what? It would be a final velocity of 0. And so our final velocity is 0, and since we're infinitely away, that term as well goes to 0. Think about it, that infinity is on the bottom. And so what are we left with? We're left with, once we cancel a few things out, right? We're going to cancel that out right there. We're left with 1/2 VI squared. And remember, our VI is going to be our escape velocity, is equal to GM over R. And the R is going to be the radius, that initial radius, wherever you're trying to shoot your little penguin off from. All right? And so, bada bing, there we go. Our escape velocity is equal to 2GM, radical 2GM over the radius. In this particular case, it would be the radius of the Earth, but it could be the radius of any particular planet. All right, what if we were a space engineer and we wanted to change the orbit of a satellite? Well, since a satellite would be in equilibrium and its U and K would be in perfect synchronicity, it would require work for us to change its orbit. And as we know, the definition of work as well as integral f dx is the change in energy of our system. And so we would, if we wanted to solve for what is the work required to change, right, we would have to do one of these guys. We've got our delta K. We've got our delta U on this side. Right? Those would all be equal to the work required to change its orbit. All right? Not much more than that, but just keep that in mind. Okay, so changing orbits again. So let's say that work has already been put into a satellite, right? Like we've launched its thrusters or whatever, right? And it has a velocity that is less than the escape velocity, so it won't get infinitely away, right? Because if the velocity was greater than the escape velocity, it would just launch and keep going, right? So if the object has a velocity that's less than the escape velocity and is not at its orbital velocity, so we're not in equilibrium, the object will redistribute its potential energy and its kinetic energy, right? And the U in this case, right? If the velocity goes up, right? You give it a little bit of oomph, right? With those rocket thrusters, right? The velocity will go down, and the U will increase, so it will become further away. All right, so if that's the case, again, we're going to start with our delta U. And this is assuming after we've already launched the rockets and it has some velocity, all right? And so what's our final velocity going to be? All right, so here's our 1/2 VF squared, and then here's our initial velocity, right? And then here's our final position, and then our initial position. This final K will be when it is at equilibrium again, right? And at that point, that's simply our orbital velocity, right? You've seen this equation before. We talked about it earlier, okay? And so you would plug that puppy in for the 1/2 mv squared. Whoa. And then you would then plug and chug, right, and figure out what the resulting R final and your final orbital velocity would be. Oh, look at this mess of a slide. We have some animations though that will pop in here. But I want to get this out, so I'm not going to bother fixing it right now. Okay, so orbital mechanics, total energy. So what is the total energy of a satellite that is in orbit around something? Okay, sometimes it's called M, the total mechanical energy, instead of just E. Okay, just be aware of that. But your total energy is simply going to be your kinetic plus your potential due to gravity, your K plus your U. And so starting with that equation, we know that our K is going to be 1/2 mv squared. And we know that at a particular equilibrium point, a particular orbit, our orbital velocity, okay, will be, and this is that same equation, all right, will be radical Gm over R. And we know that our U here, again, from what we've gone over already, is negative Gmm over R. And so if we do a little bit of algebra, we plug that in, we get this equation, Gmm over 2, positive. If we then combine those two, So I'm taking my K plus U, plugging in my K, plugging in my U. What do I get? I get negative GMM over 2. And again, this is that weird thing where it's got a negative sign in front of it, but that's okay, right? Because remember, our infinitely away U is negative. Or sorry, is 0, and therefore as you come closer, it's negative. And so you get basically some pretty weird graphs. All right, are you ready for it? Okay, this here is an energy graph. And so it is basically we are graphing what's happening, the total energy, gravitational energy, and kinetic energy at different R's. And so if we look at our expression, right, we know that our K's are always going to be positive. We've kind of done some problems like this before. All right. So our K's are always going to be positive. In this case, our U's are always going to be what? They're always going to be negative. And if you sum the two, right, you're going to get an energy that is also negative, but is closer to 0 because you're adding in this positive K. And so this is what these curves look like. There's a K curve, which is always going to be positive. There's a U curve, which is going to look like this and is going to be negative. And then there's going to be a total energy curve, right? That is going to also have the similar shape as your potential due to gravity, but be closer to that R axis. All right, and so what you notice, right, is that it kind of the U will exponentially get higher because of this R right here. All right, but it gets balanced and offset by a higher value of K. All right, these are orbital total energy graphs. We will do a couple of these. They're not as intimidating as they may appear to be. You just have to keep in mind that your U is always going to be negative. Your K is always going to be positive because you can't have negative kinetic energy. All right. Whereas with U, you can have a negative energy due to gravity, but it's always going to be relative to a reference point, and so that's why it can be negative. All right. And then of course, when you combine the two, you also get this total energy that comes out negative.